talked about Boyle's law. That was lesson 4. Lesson 4, Boyle's law, was pressure and volume. And we're going to go through all these variables. We're going to relate them. Pressure, volume, volume, temperature, pressure, temperature. We're going to look at all the different options here, basically. Each one's a different law. So today we're going to, well, part of today is we're going to do Charles' law. Okay? Charles' law focuses on volume and temperature. That's something you need to know about this. That's at the bottom here, and we'll get to that point right away here. But volume and temperature. If we're focusing on volume and temperature, we want to keep the pressure the same today. So when a sample of gas has its volume changed while maintaining a constant pressure, its temperature also has to change. As the temperature of a gas increases, so remember, one of the things you have to remember about when we talk about gases, you increase the temperature, you increase the speed of the molecules in the gas, how fast they go. That's how you control how fast they go. If you increase the temperature of the gas, you're increasing the speed at which they go. The faster they go, the more collisions there are. The more collisions equals more pressure. If you take energy away from molecules, you're going to slow them down. If you slow them down, there's going to be less collisions, less pressure. Okay? So that's what we need to keep in mind as a result of this here. Here's Charles' law here. This is what you need to know. Okay? As the volume of the sample decreases, the velocity of the molecules has to decrease as well in order to keep the frequency of collisions constant. Therefore, as volume goes down, temperature goes down. If the volume of the sample increases, we need to increase the speed of the molecules. The temperature has to go up to keep the pressure the same. Look, okay? Here's 2 cylinders here. Okay? Basically, the relationship is the volume goes down, the temperature has to go down. If the pressure remains constant, if the volume goes up, the temperature has to go up, okay, to keep the same pressure. I'll give you some scenarios here. We're talking about volume and temperature. So look, in my first one here, here's 3 gas molecules, let's say, okay? How many collisions are there going to be? Well, in this container here, enough, I guess you could say. They're going to bounce off each other here, off the sides of the wall, etc., etc. Okay? If we want, in Charles' law, to keep the pressure the same, the pressure has to be the same, right? So let's say the pressure here is 100 kilopascals, and let's say in this cylinder here, the pressure also I want to be 100 kilopascals. Obviously, in this case here, the volume's quite low, right? In this case here, the volume's higher, okay? How am I going to keep the pressure the same between those 2 containers? Let's say we just expand that one container. How am I going to keep the pressure the same? Well, look, guys, if the volume's small, how many collisions am I going to have? How far do these have to go before they bump into the side of the container or each other? Probably not very far, yes? The volume's small, right? So, if the volume's small, okay, we don't need a lot of energy to keep that pressure there, basically, all right, to keep a pressure of 100. In this case here, the volume's quite large. So how far do molecules have to go before they bump into something? If the volume gets larger, they have farther to go, yes? True? Before they bump into something, okay? Volume gets larger, they have to travel farther before they're going to bump into each other or the side of the container. Well, that means that pressure by default would be lower because there's going to be less collisions, less often, right? How do we speed up the collisions? How do we get the pressure back up to 100 in this case, for example? We give them more energy so they go faster, right? They have to cover more distance, right? So we speed them up by giving them more energy. Okay, to compensate for that. There's another little diagram coming up here which I'll show you shortly. All right? But that's how we're going to compensate for the difference between these 2. All right? So Charles' law does volume and temperature. There is a graph that goes with this as well, as always, that you need to know. The graph is actually 2 of them. There's actually 2 graphs to go with Charles' law. Volume, temperature. We're going to do one in Kelvin, and we're going to do one in Celsius. Okay. Charles did lots of experiments on gases, and he came up with this kind of thing here, and I'll kind of explain this a little bit more in the next slide here, but the graph that's displayed for Kelvin is usually something that looks like this here. Okay. And the one for Celsius, usually we just kind of extend this a little ways. Unfortunately, I'm going to run out of room here, and that would be that there. So they look kind of the same, but once again, maybe I should just draw that here. Let me do this one here, just over again. Volume, temperature in degrees Celsius, usually kind of extend this and do that. The one for Celsius, what's that number right there that we're going to talk about? Well, that's actually for Celsius, it's a negative 273.15 degrees Celsius. That would be that number right there. That's the temperature. Okay? It's kind of where that line would touch that x-axis if you want. For Kelvin, up here, for my first Kelvin one here, that would be 0 right there. 0 Kelvin. And I'll get rid of this one here, actually. It's probably not the best one. There. Okay, good enough. All right? So those are the two graphs we're going to look at, and like I said, we'll talk about this more on the next slide here, but make sure you know those two graphs. Always very good multiple choice questions. Which of these represents Boyle's law? Which one of these represents Charles' law? There might be more than one, okay? Like so. Which one represents the next one we're going to do, Gay-Lussac's law, okay? All right? So how do we come up with these graphs, or what's that, why the numbers, etc.? Well, Charles did lots of experiments with gases. That was his deal. That's what he wanted to focus on. And he found out that after he did lots and lots of tests, okay, so he got one test of gas here, he did another test, and another test, and what he basically measured here was, well, that's a very poor diagram again here. I don't know what's going on. All right, let's try that again here. So he did lots and lots of tests with different gases, hydrogen, oxygen, and neon, and all these other ones. And he found out the same thing almost with all of them. There's a direct relationship. And we're talking about, of course, the volume and the temperature here. So he said, if I want to keep these, you know, basically, if I want to do some studies on volume and temperature, he basically found the same thing. As he started to cool the gases down, they kind of followed the same linear pattern. And they all seem to kind of meet up at the same spot, okay? He said, basically, they all seem to be matching up right here at negative 273.15 degrees Celsius. And so he coined that, basically, absolute zero. He said that's absolute zero. That's where, theoretically, if you cool the gas down to negative 273.15 degrees Celsius, every gas would have no volume to it, okay? No volume. The volume would be zero, theoretically speaking. Okay. Now, that's kind of impossible, but theoretically speaking, that's what would happen. Have no volume. So that was used in part of our formulas here. Now, let me just write down. This is what Charles' law says here. That's Charles' law formula. You need to write that down. That's his formula. V1 over T1 equals V2 over T2. Okay. With this kind of formula, look at the T1 here, by the way, stands for temperature. T2 stands for the final temperature, initial final. What's a problem that can come up with having temperature down there, for example? Let's think about Celsius for a second. Degrees Celsius. What could potentially happen if we're not careful when I go to cross multiply, etc., etc.? There's two things wrong with this formula if that's in degrees Celsius. So let's say I put degrees Celsius in there. What's one possible problem I could come across? Ideas. Think about today. What's the temperature out today? 10-ish? 10 degrees Celsius? Can I put 10 in the bottom there? Would that be okay? Let's say the gas goes from 10 to 20 degrees Celsius. Is that okay? Is that acceptable? Probably. what if it's 10 degrees here, and then I take the gas and I put it in the freezer and it gets down to minus 20 degrees Celsius? Any problem with that in this formula? What's going to happen to the volume if I'm solving for volume? 10, and I go down to minus 20. So I put 10 in here and I put minus 20 here. What happens to the volume? When I solve for V2 or V1, it's going to be negative, correct? 10 minus 20, cross multiply, you're going to get a negative volume. That doesn't make sense, okay? If I have 100 milliliters of gas, I'm not going to get negative 20 milliliters of gas. That's impossible, okay? So we have to have everything positive, right? What's another problem? Think of Celsius. Work with me here, people. Think of Celsius. What number could possibly go into there that would kind of really mess stuff up on the Celsius scale? Yeah, 0 would be a bad number to put there because anything over 0 is undefined, yes? Okay. So, because of those two things, we don't want to use Celsius down here. Okay? That's what number 0.3 is. The temperature the temperature of the gas has to be measured in Kelvin. So, how do we get away from that? Well, Charles said, hey, if 0 volume happens at negative 273.15, I'm just going to adjust the scale. I'll call negative 273.15, I'm going to call that 0 Kelvin. Anything above there is positive and more than 0, because theoretically we'd have 0 volume, but probably not going to happen. So 0 Kelvin, everything's got to be above that. If we change the temperature into Kelvin for every formula we do this year, we get away from negatives, we get away from zeros on the bottom, and that's a good thing. So that's where they came up with the scale from. Okay, that's the Kelvin scale. Came up with that because once again, we're changing all the negatives and the 0 into positive numbers. Okay? So, for any formula, listen to me, write this down somewhere for crying out loud because you're just a bunch of zombies right now. Any formula you do this year, if it involves temperature, it's in Kelvin. Simple. Temperature has to be in Kelvin for any formula this year. Okay? Temperature has to be in Kelvin. You can use this formula. This is Charles' law, V1, T1, V2, T2. By the way, if these three conditions are met, which of course, we're talking about volume and temperature, so the pressure has to be the same. Closed system, you can't let any of the gas escape. Temperature has to be in Kelvin. Here's a better diagram of, for example, what happens if we're going to relate Charles' law here. So here we go. This one here says, hey, you know what? The pressure of the atmosphere is pushing down on this cylinder here, or this plunger, okay? That will equal the pressure on the inside. By the way, inside this room, I can tell you right now, if we were doing this, the pressure on the outside, the pressure of the atmosphere around us, is usually about 101-ish, 0.1, 101.2 kPa. Okay? Now, if we had a jar sitting right here with a plunger that moved up and down freely, okay, I'll tell you right now that inside of here would be 101.2 kPa, or sorry, 1 kPa. Same as outside. Why? If it wasn't, what would happen? If those two pressures aren't equal, what's going to happen to the plunger? Yeah, depending on what it needs to do to equalize out again, yes? And in fact, if the pressure in this room is 101.1, I guarantee you that plunger will move up or down, depending on what it needs to do, so that the inside part equals 101. Because if the outside part's 101 and it's 90 in here, it's going to go down until those two equal out, right? Why wouldn't it? If the force on the outside is greater than the force on the inside, it's going to push down until those two forces equal. Or if it's 200 down here and it's 100 up here, it's got to expand until those two equal again. Okay? So that's how we start out here. Pressure of the gas is equal to the pressure of the atmosphere. That's something we're going to use for our first lab when it comes time, which is shortly here. Okay? So that's the first thing. Then guess what? You got all these gas molecules. Hey, I'm going to put it on the stove. I'm going to start heating this sucker up. So I start heating this up down here, right? I put this on a stove. Ooh, hot. Actually, I should use red, right? Red, hot. Ooh, so hot. Getting hot. Song about that. It gets hot. What happens to the gas molecules down here? They start going crazy, right? They start speeding up. They're going quicker, quicker, quicker. There's more collisions. More collisions equals more pressure, right? Look, more pressure, right? How much pressure? I don't know. Maybe it gets up to 200, maybe 300, maybe it's 150. But there's more pressure down there. Well, is the outside part equal to the inside part? No. Let's say this gets up to 200 here. This is still 101.1. Those two aren't equal. What has to happen? They have to equalize. How does that happen? The volume has to get larger. Volume goes up. Why does the volume go up? Well, because there has to be less collisions, right? If this is still 101.1 here, this has to equal 101.1. How does it do that? It expands so that those gas molecules that are going faster have less collisions, right? There's more space in between them now. They got farther to go. They're going faster still, but they got farther to go now before they run into each other, okay? That's what Charles' law is all about. Volume and temperature, how they're related, okay? Keeping the pressure the same, all right? So that's Charles' law. Good? Questions? Anyone? Yes, no? Don't know?